Well, I'd like to thank, of course, the organizers for inviting me to be here in this beautiful place to give this talk. So I'm going to talk to you today about an experiment. I'm an experimentalist, and I'm going to talk to you about an experimental probe basically borrowed from the world of mesoscopics to try and access the underlying low-energy current-carrying excitations in a strange metal. So, you know, we all know this kind of story. We've heard much about this earlier today, so I won't belabor it. But, you know, we're making little tiny devices. We're not using focused ion beam. We tried, and it didn't work well for us. I'd be curious to talk to the previous speaker and read their review article on that. But the bottom line is that we're seeing some interesting things. So let me tell you the story. But before I do that, I should say, of course, all of this work was really done by a large group of people. The real heroic person who is now working for Barclays, making more money than me, is my student Liang Chen. And an earlier version of this paper is up on the archive. And there's some related theory work that is also up on the archive, and the DOE largely paid for this. And this work couldn't really have been done at all without the group of Professor Silke Paschen from Technical University of Vienna, because they're the folks who figured out how to grow beautiful epitaxial films of the material that we like to use. So the material we're working with is a terbium-rhodium-2 silicon-2. This is one of these quantum critical strange metals. And there is a quantum phase transition at low temperatures to really see the quantum critical fan spread out. I didn't point out the temperature scale on the color plot on my title slide, but you basically have to get below about 100 milledegrees to really see this nicely. You have a low field phase that has antiferromagnetic order among the terbium local moments, and you've got long-lived, relatively heavy quasiparticles, but this system is a Fermi-liquid. It's got a relatively small Fermi surface. And then this is one of these condo destruction quantum critical points. So if I crank up the field and the critical field scale is a little bit under a Tesla, you actually end up on the high field side in a paramagnetic, so you've destroyed the antiferromagnetic order, a paramagnetic heavy Fermi liquid with a large Fermi surface. There's been a lot of work done in this system over the last, say, 20 years. And in between, there's this big quantum critical fan. And in this big quantum critical fan, rho really does go like a residual resistivity plus a linear NT piece. And you know, people have looked at things like the heat capacity and so on, and it satisfies sort of all of these things that we now like to call strange metallicity, broadly speaking. And of course, one of the big questions is, you know, how should you think about the low energy excitations in a system like this? There's a lot of fairly exotic things that have been discussed. And you know, one question that intrigued me is, what kind of experiment could you do to really try and get microscopic information about the underlying degrees of freedom? The challenge with things like photo emission and so on is that, you know, or tunneling measurements, is that you're yanking out entire electrons, right? And this is a pretty brutal thing to do. And so one of the things I was very interested in was, is there something we can do that keeps the charge carriers within the material, within this special environment, and yet still get some microscopic information about them. So let me tell you a very little bit about noise. So, you know, the theorist fantasy, I like to say, is, wouldn't it be great if I am doing an electronic transport experiment and I could tell you the arrival time of every single electron? I can just come up with an ordered list of, you know, electron 1 came through at such and such a timestamp. We can't do that, but we can do better than just I versus V. Once you drive, so in equilibrium, of course, you have Johnson-Nyquist noise. This is just due to the thermal fluctuations of the occupancy of the electronic states, and as a consequence of the fluctuation dissipation theorem. But once you drive a system out of equilibrium, you actually get an extra contribution to the noise. And this was originally worked out by Schottky over 100 years ago, when he was worrying about the noise in vacuum diodes. And he just did the statistics problem of saying, okay, I've got some electrons. I'm just going to say there's an average arrival rate for electrons. This one doesn't know when the next one's coming. It doesn't know when the last one came through. They're just a Poissonian process in terms of their transport. If you carry that through, you find that the current fluctuations per unit bandwidth end up being basically white in frequency. So this is the current noise. And so this really is the mean square fluctuations in the current per unit bandwidth. The units on this are amps squared per hertz. And it's just, it ends up being twice the electronic charge times the average current. And this is just a consequence of the fact that charge is coming in discrete lumps and charge is granular, and there's just statistical fluctuations in the arrival times of those lumps. And now, of course, what if the electron arrivals are not independent? Well, more generally, when you actually do a measurement, people like to actually compare what you really measure with this Poissonian result, so that this ratio between what you measure divided by 2EI, that gives you this thing called the Fano factor, because Ugi Fano has his name on lots of things. So in tunneling, this is pretty well well known, the sort of thing that you see. So at zero current, right, at zero bias, your current noise just looks like 4 kT over R. This is just the Johnson-Nyquist thermodynamic equilibrium noise. And shot noise in this context is sometimes called excess noise, because as I crank up the current and drive the system out of equilibrium, I get additional contributions to the noise. Okay, so now if I don't get any additional contribution to the noise, you would say the Fano factor is 0. I'm only ever measuring Johnson noise. So there's a couple of different ways this can happen. Clearly, if the electrons came through perfectly evenly spaced in time, that would suppress the noise. If charge was a continuous fluid and there was no discretization of charge carriers at all, that would also suppress the shot noise. Again, the Fano factor of 1 is just sort of this Poissonian arrival of individual electrons. And of course, if I had like the Poissonian arrival of pairs of electrons, I would see a Fano factor of 2. And so people have used shot noise. I have auxiliary slides. People have used shot noise to demonstrate things like apparent fractional charge in the fractional quantum Hall effect by looking at the Fano factor and edge state backscattering, edge state tunneling. So it's an interesting question, how electron-like are your quasiparticles? Now, again, I'm not going to tell you about a tunneling experiment, but you could imagine, what does it mean if there are no quasiparticles? Does it mean that the Fano factor is 0? Does it mean we have effectively a continuous fluid? Things are a little more complicated, as Subir alluded to this morning. So let me show you how this works. The specific thing I want to do is not tunneling, because I didn't want to yank whole electrons out of the system or dump whole electrons into the system. I'm relying on a result that is not all that well known, but it's a very pretty result from sort of the world of mesoscopics in metals from 25, 30 years ago. The idea is the following. I'm going to make a constriction, a diffusive constriction between big fat leads, okay? And so I'm going to look at the current noise in this constriction as I drive the system out of equilibrium. And there are some interesting limits. So if the device length is short compared to electron-electron scattering lengths, so the electrons don't really have a chance to exchange energy with each other, right? In that limit, what you find is that the Fano factor, this measured noise over 2EI, the Fano factor is 1/3, okay? And I'll show you data that supports this. But this was originally measured, back in the 90s in things like gold and silver. Now, if the electrons are able to exchange energy with each other, so maybe either the electron-electron scattering is stronger or the device is a little bit longer, so that somehow the electrons can basically locally thermalize inside the material, then you have effectively a locally elevated electron temperature. This is all derived using kind of a Boltzmann formalism. And what you find is that in the absence of electron-phonon scattering, then what you find is that the Fano factor is supposed to be square root of 3/4. So it's even bigger. You get more noise, okay? Now, this has really not been seen clearly. There's an experiment in graphite, or bilayer graphene, I should say, where they see things close to this. But it's actually pretty hard to get in this regime, right? And now if the, going back for a second, if the device is so long that the electrons have enough time to really talk to the lattice and dump energy into the phonons, then that can suppress the noise. And very heuristically, you can see why this might be the case. Imagine that the electrons are really strongly coupled to the lattice, so that they're always distributed like a Fermi-Dirac distribution at the lattice temperature, no matter what you do. So if that was true, then you'd only ever measure Johnson-Nyquist noise at the lattice temperature. Yes?
It's another lens that which should be somewhat there, just mean free path due to impurity scattering.
Right, so that mean free path, I should have mentioned it, that mean free path is way down here. And so
That is because you know that mean free path in your material? That doesn't
yes,
have to be that.
it doesn't have to be that.
That's the longest.
Yeah, yes, right. So you're absolutely right. You could have a situation where you basically have ballistic transport. Right. We are not in that limit.
Okay. So you are assuming that to be the shortest length, that's why not showing up here.
That's correct. Okay. That's correct.
You also say one is never measured?
One
is never measured?
One is never measured in a diffusive constriction. One is totally measured if you do tunneling experiments. You can see a Fano factor of 1. If you just make a generic, if you just make a generic vacuum tunnel junction with an STM tip, or you can make like a gold, HBN gold tunnel junction or something like that, you totally can see 1 as the Fano factor. Or there's an undergrad lab exercise where you can actually use a vacuum diode and you absolutely see 1. Okay. So, keeping an eye on the time here. So, just to spoil it a little bit, so we went and we made one of these gold constrictions, right? So here's an SEM image. Here's a little gold wire. It's pretty narrow. That's a 500 nanometer scale bar. Big, fat, thick gold pads on either side. And here is the noise. Now I'm actually plotting voltage noise because that's what we actually measure. I'm happy to talk about the technicalities of how we do the measurement. For reasons of time, I didn't want to dwell on that, but I'm happy to talk about how we actually do the measurement. Basically, you can take the current noise and multiply by the differential resistance squared and convert it into voltage noise. What you see is the upper dashed line is basically the analytic expression for finite temperature smearing, finite bias, Fano factor equals 1/3. Okay? And what you find is, yeah, it really works very, very well to describe the data. And again, we sort of expected this. This is what you should see. This is what's been seen previously in something like gold.
So just to make sure, so you're applying current measure voltage, so you work on the current bias.
Correct. Yes.
The only free parameter is Fano factor.
In the fit, you measure everything else. The only thing you're adjusting is the Fano factor. That's right. And it's particularly simple in the case of the gold as well because the wires are extremely ohmic. So you don't have to worry about the differential resistance really changing as a function of bias or anything like that. I'll talk more about that in a minute. So, as you raise the temperature, this Fano factor does drop a little bit, but I mean, it's pretty robust, even up to like 20 Kelvin. I'm assuming, I don't know for sure, but it's entirely plausible that, eventually the phonons really turn on, and you really ought to suppress the noise because of electron-phonon scattering in the system. Because of the.
Why couldn't we go to higher temperature to see that? The thing that you're assuming, why didn't you make it a fact?
You can go to higher temperatures. There are some other challenges going to higher temperatures. The Johnson-Nyquist noise, of course, is going up as you're going to higher temperatures. But we could have gone higher. Right? I mean, the biggest reason we didn't go higher, honestly, is that we're trying to compare this to the non-Fermi-liquid, and there's no point in going higher for the non-Fermi-liquid.
Right. I was just wondering whether the Fermi-liquid behavior is established before I worry about non-Fermi-liquid.
Right.
If you tell me you don't even know whether Fermi-liquid behavior at high temperature is established of electron-phonon, I remain a bit skeptical.
Well, I can say, I mean, we know for certain that if you try and do this measurement at 300 Kelvin, you don't really see much of anything. So somewhere between 20K and 300K, everything it does go away. Yeah.
That's good enough for me. Thanks.
Even in this narrow wire, your elastic mean free path is larger than 500 nanometers?
No, the elastic mean free path is shorter.
Sorry.
It's the short, yeah. Right. I will say it's a little bit more challenging to estimate the elastic mean free path in the strange metal. In this stuff, we know the diffusivity of gold, we know the resistivity. You can just use like the Einstein relation and the Fermi velocity for gold to back out a good solid number for the mean free path. Okay. So again, like I said at the beginning, part of the magic here is that Silke Paschen's group knows how to actually do MBE of these rare earth intermetallics, at least this one. And they grow these things on germanium substrates, which by the time you get down below about 150 Kelvin are completely insulating. I do want to, so once we've got these nice films, we can imagine doing lithographic processes to make little wires. I do want to point out, because I realized I hadn't said it anywhere else, in the temperature range we're working with, which is basically, for some technical reasons, 3 Kelvin and up, the quantum critical fan extends across all available field that we can get to. We've done these measurements at 0 field and at 9 Tesla, no difference, right? And that's not surprising based on the properties of here. We are working on trying to do this in a dill fridge in Europe. It's very challenging. Again, we can talk about that if you want. Okay, so my student figured out a way of basically patterning this stuff using chromium as a hard mask. This is one of these cute material science things. When they grow bulk crystals of ytterbium-rhodium through silicon-2, they use hydrochloric acid to wash away the residual flux. So we knew that this stuff wasn't going to go away if you dunked it in HCl, and so we could use HCl to strip away the chromium. Anyway, he came up with a nice way of doing this process, e-beam lithography processing. And you can make structures where, here's an electron micrograph. If you zoom in, there's the little wire. The edges on this particular device look a little rough because of the way the etching works with the gold, the big, fat, thick gold pads. But the thing I want to convince you of is that this is normalized resistance, normalized to what's happening at 100K. One of the big questions we had was, does patterning these things into wires ruin them, right? And what we found actually was when we tried to do FIB, we were running into all kinds of problems. But when we do this reactive ion etching method, it seems to work pretty well. R versus T for the unpatterned film and the nanowire device, once you normalize by what's going on at 100K, they look basically the same. The magnetoresistance for an in-plane field, basically pointing this way, I don't know why it has the shape that it does. I mean, we can speculate about that, but the point is that it's basically identical with and without the patterning. So we're very confident that we can pattern this material and not ruin it. And R versus T is actually linear in T at low temperatures. Remember, this is a normalized thing. It does turn out the residual resistivity actually does go up if you actually pattern it because you're introducing some amount of disorder.
The main figure looks very hot. Doesn't look like linear in T at all.
Well, it's linear in T down here. What you're seeing up here is the conductivity in the germanium substrate turning on.
Yeah, not all the way up here. It's bending already. So I should think of the lowest part of this.
So the condo energy scale in this material is about 25K. So you should only reasonably expect to see the linear T resistivity below 25K or so. But this is very, very similar. I mean, with this accepted, this is very similar to what people see in the bulk if you grow bulk crystals of this stuff.
What does it become T squared eventually, which it does in this material?
Like 45 millikelvin or something like that.
45 millikelvin.
It's very low. Yeah. Don't quote me on that. It's something low, well under 100 millikelvin. Way below this, right? So here's the main result. You go and you do this measurement, and you find at 10 Kelvin the final factor is darn close to 0. As you cool, the final factor goes up a bit. But remember, you might imagine in this material where everyone who studies it seems to think electron-electron scattering is extremely strong and extremely important. You might imagine that you should see the root 3/4. We do not. Okay. So we've seen this in multiple devices. We've seen it, as I mentioned, in all these different magnetic fields. It's quite robust. So what's going on here? So you might wonder, since I mentioned that phonons can kill you, you might wonder, is this all due to phonons? The short version, no. So you can model this. This was, again, these folks who were looking at this back in the 90s on ordinary metals. You can come up with if you make a really long wire where phonons are important. And by long, I mean 50 microns long, okay? Phonons are important. You can come up with a little toy model, doing it as a 1D problem of the local electronic temperature. You have some electron-phonon coupling, and there's some local electron temperature, there's some lattice temperature. You can go, this basically is assuming Wiedemann Franz, I should say. You go through and you do the calculation, and the point is you can actually measure the noise as a function of the current and back out this number gamma. And if you do this, and I've got supplemental slides on this, if you do this, the literature value for gold is about 5 × 10⁹ in these units, and we get the same number, okay? So you can do the same experiment in the ytterbium-rhodium-2 silicon-2, make a really long wire, do this. bottom line, things are a little more complicated because R versus T is now linear in temperature. It's not basically sitting at the residual resistivity. But you can do exactly the same thing. It actually even this correction doesn't really do much for you. And what you find is...
if you don't see phonons in DC transport, how do you know gamma R, for example? How do you know electron-phonon coupling?
So the idea is that in these very, very long, you assume in these very, very long wires that there is some electron-phonon coupling eventually, right? And that because you know that there has to be. And so, I mean, in some sense, the concern is the suppressed shot noise due to strong electron-phonon coupling. And so we're just trying to do the simplest measurement that will give us a crude estimate of electron-phonon coupling. And so I don't know if that exactly answers your question.
To be much larger than the electron phonon being feedback.
Right.
And presumably 50 microns satisfies.
You think 50 microns ought to be safe.
Even at this temperature.
Right.
That's really the point.
Right. And the fits, if you measure, noise as a function of bias current in these really long wires, the fits are gorgeous. The only adjustable parameter is gamma in this model. And you get a gamma that, it's a bit bigger than the case for gold, but not much bigger. And I do want to point out that if you say, well, what if, suppose I artificially crank up the electron-phonon coupling, how big would it have to be to explain the suppressed noise? And the answer is it would have to be like 68 times larger than the value in gold, which is kind of physically unreasonable and completely different from what we actually measure. Also, it's worth noting the Debye temperature for this stuff is twice as large as that of gold. So again, you really don't think phonons are playing a big role down where we're working. So so we can conclude the noise suppression is not due to phonons. Are there issues with the fact that the wire is a little bit non-ohmic, right? There is some, there is some non-ohmicness to the wire. The short answer is no. I mean, the noise is robustly small, so you can fit it in different ways, trying to correct for in interesting ways for non-ohmic behavior. This is actually pretty complicated. So here's the fit we used initially, where you basically just use the differential resistance everywhere. You have to be very careful doing this. Here's the fit where there's a literature thing on what to do if the wire is a little bit non-ohmic, and so we can do that. And then there's another expression that implicitly deals with things being not ohmic by just, instead of differential conductance, it just puts I over V in there somewhere, right? So these are different ways of analyzing non-ohmic devices, and I'll cut to the chase. The bottom line is all of, again, the data are what the data are. The fits all look quite good. All this does is it changes your fit parameter, and if anything, including all these non-ohmic corrections makes the phono factors even smaller. So, bottom line, these devices are kind of anomalously quiet, and the noise does go up a little bit as you cool down, but we're well below the Kondo energy scale in this system, so it's not clear. Exactly what's going on is an interesting question. You might ask, okay, could there, and again, maybe with the number of theorists in this audience, maybe this is a silly thing to say, but you might wonder, is this just like a finite temperature Fermi-liquid correction of some kind, right? And the answer is, if you go and you really try and do, because all the theory that was done in the 90s on the mesoscopic stuff was kind of really sort of for a Fermi gas, not a Fermi liquid. But it turns out if you actually go through and you really carry through the Landau parameters, basically everything cancels out. The quasi-particle weight Z never shows up in the calculation. And a strongly interacting Fermi liquid is still expected to give you this root 3 over 4, which we do not see. So, how should you think about this? I mean, what do we think is going on? Well, I think it's tempting to suggest that basically in something like gold, we're in this diffusive quasiparticles, weak electron-electron scattering limit. I would have expected us to be up here if we've got really well-defined quasiparticle excitations that just scatter off of each other all the time. But instead, we seem to have a more complicated situation. Now, you could imagine if I truly have, like I said before, a continuous fluid with no dispersive modes at all, that I might get a temperature-independent phono factor of basically 0. We don't get that, right? And again, there's been, I've got a couple of slides. Subir has been one of the people working on alternate ways to think about the strange metal. But I would say that the greatly suppressed noise, I think it's not due to phonons. It's not due to finite temperature Fermi-liquid effects. I think it implies that there really are not well-defined quasiparticles in the system. Now, there's some obvious next steps. Clearly, it would be great to be able to field tune in and out of the strange metal state, to be able to dial in the non-Fermi liquid behavior in a single device, right? We're working on that. We're playing with a couple of other materials, including terbium rhodium 2 silicon 2 at lower temperatures. It would be great to actually work in just a strongly correlated Fermi liquid that is a Fermi liquid, but we know the scattering is really strong, and see if we can see the root 3 over 4. So anyway, there's still a lot to do. With that, I will put up my acknowledgments one more time, I have a couple. I have one interesting thing that one of the referees on the paper wanted us to include. I'm happy to describe it for you in a second if you're curious about it. Thank you.
Let me make a possible suggestion.
There you go.
So this factor of 68 between that you mentioned, this is not a result that depends just on electron-phonon coupling. I mean, I spent all of 1980s working on hot electron relaxation, which is a very big problem, okay?
Yep.
It depends on all the electronic parameters, like Fermi energy, electron effective mass. It's an electron-phonon coupling, and for example, in graphene, electron-phonon coupling depends inversely on Fermi velocity. So if the Fermi velocity goes down by a factor of 10, this gamma will go up by a factor of 10. So based on what you told me, I know nothing about it, and I heard about the work, but I didn't read it. I remain unconvinced that factor of 60 could not come from phonon effects, because it's a matter of calculational details. Again, maybe somebody has done this very honestly and ruled it out, but not based on what you told me.
So what I would say to that is, I believe you that you could have anomalously strong electron-phonon coupling. I'm saying you can do an experiment that's supposed to measure the electron-phonon coupling, and it tells you that the electron-phonon coupling experimentally is weak.
But it's not the coupling, the energy loss we're talking about. It's not electron-phonon coupling. The capital gamma is not an electron-phonon coupling constant.
It is an energy loss.
Energy loss rate.
It tells you that the energy loss rate is weak, experimentally.
Oh, did you show us that experiment? I didn't understand. You showed us that experiment.
I did, yeah. We measured gamma, and you can experiment. I'm happy to talk about it offline, but you can infer gamma, that energy rate, and the gamma is about a little bit less than twice as big as for gold, but it's not 68 times gold.
Doing similar experiments.
Yes,
long wires.
exactly, same experiment.
Yeah, thanks for the very interesting talk. I mean, we should chat, because we did fib YRS, and that works very nicely, especially for shock noise measurements. But I have a quick technical question and somewhat of another. So from a technical point of view, how high is the resistance of your wires at low temperature? Just to get an idea.
So the resistance of these wires was about 30 ohms.
30 ohms. Okay. And the other part is that should we be worried about the epitaxial interface to the substrate? Is this a loss mechanism for phonons, especially for inelastic scattering into the bath? Because we're discussing now phonon scattering within the material itself, right?
So again, I think this long wire experiment should actually be sensitive to that too, because it's just sensitive to energy loss out of the electron system.
Yeah.
So I think if you were losing energy to the world, you would know, I think. So I think, though I mean, whoops, sorry.
How?
I hit the button.
Sorry,
well,
maybe I missed that.
So
you see the counter factor vanish, which you do.
Yeah, well, okay. So in the very long wires, I mean, I would think you would, if you basically saw very, very efficient coupling to the world, right? You should not get this increase in the noise at high bias as a function of bias that we kind of fit with this simple 1D model. It should look different if you're getting local loss to the. I mean, it should sort of masquerade as an effective increased gamma, I would think. We can talk about it.
Okay, thanks.
Doug, just clarification. So for this √3/4 limit,
Yeah.
Theoretically speaking, this applies when electron-electron mean free path is short compared to the wire length. So suppose that I give you Planckian limit and whatever the Fermi velocity should be in that. So you probably did the calculation and it's short compared to the length scale of your wire. Is it or it isn't?
That's a really good question. I think it depends critically on what you use for the Fermi velocity.
That's
and of course, the whole point is that this quantum critical regime is sort of between the large and small Fermi surface situation. So it's certainly kind of the same order as the length of the wire.
Well, okay, so the reason I'm asking is that these two extreme limits, 1/3 or √3/3, has very specific forms of the distribution functions.
Yes.
It's not always reducible to whatever the effective temperature is.
Yes, I agree.
And so then you could sort of engineer the factor depending on non-equilibrium conditions.
Yes.
And too quick, do you have by any chance measurement at different wire lengths?
Yeah.
Do you have by any chance a frequency dependence?
So I'm sorry.
Of noise.
The frequency dependence?
Of noise, yes.
So the frequency dependence that we're doing all these measurements basically at a few hundred kilohertz and below, and the noise is effectively white, except for the fact that our wires act like an RC filter, so you get a roll off at high frequencies because you just capacitively attenuate the signal. These measurements in the long wires, that's the thing that we use to get that gamma estimate. And so I could go back if you want to see. Let's see here. There. That's an example of noise as a function of bias current at 3K, 5K, and 7K in this very long wire. And like the dashed line, this is the fit to that simple 1D model with the energy loss rate, gamma. And like the only adjustable parameter is gamma. So.
Yeah. So Doug, in this material, the Hall resistance also changes abruptly, right? And as a
if you're cold enough,
yeah.
You can yes, the Hall resistance. There's a discontinuity in the Hall, right?
So at the lowest temperature where you measure shot noise at 3 Kelvin, is that fairly abrupt or it's broad? It's very broad. So that's corroborating the width of the quantum critical.
Doug, intuitively, such a strong temperature dependence isn't pronounced the simplest way to look at it?
So, except for the fact that you can measure I mean, it could be, except that there's other reasons for thinking that the phonons should not be relevant by the time you get down to a few Kelvin. High Debye temperature, various other measurements of thermal conductivity, for example, right? And so there's that piece, and then there's the fact that we try and do this measurement of gamma. Now, if there's something really weird going on, then maybe nature is messing with us, and there's some weirdness happening. Maybe a better way to say it is, if my charge carriers are strongly coupled to some kind of bosonic bath, and that bosonic bath is sitting at some temperature that's close to the lattice temperature, then that would do this. It just may not be actual phonons, right? Do I have 30 seconds to show the weird thing?
30 seconds. Cameron has a comment.
Oh, sure.
Go ahead. Cameron.
So my question was about you. As you said, all this quantum critical phenomena happens at very low temperature.
Yeah.
The nail temperature is like 70 millikelvin, something 45 millikelvin.
Correct.
So is there any technical reason not to be able to do this measurement in a dilution fridge to see?
So we're trying to do it in a dilution fridge. One of the challenges is that if you looked at the currents we had to get to see the shot noise, right? Like if you do this, if you cool the sample to 30 milledegrees and then shove 100 microamps through it, you're not going to be at 30 milledegrees. So what you really want to do is do the measurement at much lower currents and use like a squid amplifier or something like that as a very sensitive voltage amplifier. That's really what you'd like to do. Like the way we're doing the measurement would not work well just slapping it on a dilution refrigerator.
Because I just have a comment about this absence of quasi-particles, because you see Wiedemann-Franz law and the deviation of it was measured by 4 different groups.
Yep.
There is a deviation, but at 3K, 4K,
there isn't. Yeah, yeah, it's small.
you recover the Lorentz ratio, and there are.
Doug wanted to say something.
I just want to show.
There's also 2. Can we make it really quick questions? So in the very back, quick question, quick answer, quick question, quick answer, and Doug gets 30 seconds.
Okay.
All right. So this was a question about the calculation of gamma. So
yes.
There you're fitting to t to the 5th, differences in t to the 5th between electrons and phonons. Is that clearly the correct thing to fit to for this material? In the sense, I assume that's Joule heating, assuming like a block Renaissance form.
Yeah. Yes.
It might be t cubed, for instance.
So we played around with this a little bit, and if you play with that power law, the fits to the data look a lot worse.
I see.
But I mean, if it was t to the 4 or something, or t to the 6, you could probably fudge some.
Yeah, it's just that since the actual resistivity is t-linear, you don't know what the correct power is.
Sorry, but this is not T5 in the resistivity. This is the T5 in the cooling rate.
Of the phonon contribution.
Right,
so.
right.
Nice talk. Do you see the suppression of fan effect similar to what you see upon increasing temperature when you raise the bias, when you raise voltage bias?
No. This actually leads into my weird thing. No, yeah, no, not really. Well, it gets a tricky thing because, like, you know, a lot of what we measure is almost kind of in this crossover. Like we're never in a super high bias limit relative to the temperature. So we don't, and also there is some change in the differential resistance of the device at high bias, so it's a little complicated. But we don't see a big suppression of the, we don't see a large suppression of phono factor at high bias. Let me show you here's the weird thing, okay? We'd relegated this to the SI, and one of the referees was like, you should mention this in the main text. Okay. There is a paper, right, on a completely different quantum critical system, superconductor insulator transition, all right? This is, now what's interesting is this is an example of a system where, again, it's a quantum critical system, and basically there's some effective temperature that shows up as, you know, as if you're doing Johnson noise, and the effective temperature has this funny, you know, crossover between KT and the electric field. And if you go and you actually, even though this shouldn't apply to our work at all, if you go and you do the fitting, it totally threads all the data. It's very, very strange. So it is a model that explicitly lacks quasiparticles, but does predict non-zero noise with a non-trivial temperature dependence. So that's actually interesting. I don't think that this model should be relevant to our system, but it's kind of weird that this does this. I mean, if I was an unscrupulous person, I would have titled the paper "Observation of Hawking Radiation" in the lab.
May I ask a question, Doug? May I ask a question? Hi, Doug.
Hi.
From the linear heat or the close to linear T log T heat capacity, is it correct that the effective cutoff in the problem is about 10 Kelvin?
I think it's more like 25 Kelvin according to Chinyao, but yeah.
Okay, within factors of 2. Okay. So if there is a cutoff on the scale of 20 Kelvin, and if there is a linear resistivity with a T log T, you would expect the Fano factor to go to 0 on the scale of the cutoff, which I estimate in this material to be 10K, but it may be 20K. That's just what you already stated. All the fluctuations are at low energy, and they are on the scale of this cutoff, which is 10 to 20 Kelvin.
I have a slide on this, but we're way past time.
So anyway, the comments appreciated.
Yes.
Let's thank Doug for the talk.
Thank you.